All right, everybody. We got a good weekend. Welcome back. I'm good. Thank you. We have more than enough. We're tense galore. All right, so let's see. I hope everyone received working on the problem set. We have our usual office hour this week, and just because I always directionally just challenge sunsets in the west. So the sunset room, I said it was the southeast, but I meant that, of course we're in the southwest. Where else would it be? So anyway. All right. We talked about, we will continue to talk about in many different ways the physics really associated with the generation of squeeze light. That's what we're really going to be interested in, generally non-classical light. Okay? And so we're looking at this from the point of view of a kind of scattering picture, whereby we imagine we have our resource to start is to have some strong laser beams that we can shine on stuff and other light comes off. Okay? The matter inside here radiates, and in doing so it scatters input light to output light. All right? And the description, when you think about this in the usual kind of electric dipole approximation, that the radiating current is oscillating electric dipoles. Okay? And so the density of dipoles, of course, in Maxwell's equations we call P, the polarization density. Okay? Right. So in a kind of perturbative limit, where we say that the strength of the polarization, the dipole that's induced, the induced dipoles in this system are small in some sense, that the electric fields inside the pump are small electric fields compared to the binding energy inside the material, then we can look at this in a perturbative limit and think about the radiating current in this kind of power series expansion in terms of powers of the electric field. That's our standard description in classical nonlinear optics. Okay? So we treat, there's a term that is the one that we're most familiar with, the linear term, which gives rise in a kind of Lorentz oscillator model where we have linear response. And then there are correction terms beyond that when we have a sufficiently strong field and we have this kind of power series and the proportionality constants are the susceptibilities that we call chi2, chi3. Guess what comes next? Chi4, you got it, etc., etc., etc. Okay. Now this is a little bit, this equal sign, really has a kind of quotation mark around it in the sense that, really this, what the hell do these vectors mean next to one another? We're talking about potentially tensors with lots of indices. We're also potentially and typically thinking about this proportionality is really only true typically in the frequency domain. It's really a convolution in the time domain because the response is a thing at a particular frequency, and it might have spatial dispersion as well. So all of those things I'm kind of sweeping under the rug, and this is not a course in nonlinear optics, and I couldn't teach one even if I wanted to. Well, I guess I could, but it would take a lot of work, and I don't want to do that. So anyway, we'll just say equals, all right? All right, so in particular, if we're thinking about, first of all, the linear optical term, Well, that term is going to have, if I look at, the interaction Hamiltonian, the P dot E term is going to have things like E and E, which will have A's and A daggers in them. And the only terms that survive when we think about this as a scattering going all the way from t equals minus infinity to t equals plus infinity are the terms that are energy conserving. And so they're, in linear optics, when we scatter off of linear material, we don't change the frequency. Okay? And so the only terms that survive are ones that involve annihilating a photon in one mode and creating it in another mode, or maybe the same mode, right? That would represent a phase shift that would occur on that mode. Otherwise, it's just some kind of transfer of the field from one mode to another, okay? And that Hamiltonian generates a scattering matrix, or an S matrix, or time evolution operator, if you want to call it that, which has this form, which is the characteristic of linear optics. So linear optics is characterized by the fact that the transformation on the modes, represented by the creation and annihilation operators, is just linear. Okay? So that's the quantum mechanical description of linear optics. Voila! Is this kind of transformation. Now this matrix, lambda here, is the, if you want, you can call it the transition matrix, or the transfer matrix that you would get from classical optics, wave optics, of how the field amplitudes transform through a linear optical network, whether it be a bunch of phase shifters and beam splitters. That's all we got when it comes to this kind of passive linear transformation. So for like a 2x2 matrix would represent this beam splitter transformation for linear optics, okay? And, the matrix elements here are the for the beam splitter are the transmission and reflection coefficients associated with that beam splitter. And this matrix, assuming everything is lossless and there's no gain, is unitary. Okay? Okay. So one thing we saw, maybe not with the most elegance in my derivation last time, don't know why, but we could do it, if you do it right. And one finds that if my input state is a coherent state, which means every mode is in a coherent state, and you put it through a linear optical network, then the output state is, as expected, also a coherent state, with the amplitudes transforming exactly as they would classically, right? So if this matrix is telling me how the electric field classically, just from classical Maxwell's equations, how the electric field of these output modes is related to the electric field of the input modes, if I put in plane waves into those modes. And the exact same thing happens quantum mechanically, now described in terms of coherent states, where the eigenvalue of those coherent states are just rescaled versions of the classical electric field amplitudes. Is that clear? Very important point here. So the wave description here is beautifully carried over in quantum mechanics. Nothing unexpected happens. Now, another thing to notice here, importantly, is that the photon statistics are unchanged. That is, we had Poisson statistics on the input, and we had Poisson statistics on the output. Why does that even, why might we even guess that that would make sense, that that should happen? I mean, in this case, we can think about this. Let's say, for example, as an example, let's say I just put in a coherent state or a laser beam into this one port, right? Then what's going to happen to each photon when it hits the beam splitter? Well, it's going to randomly, with some probability amplitude, transmit and some probability amplitude reflect. Or we could say there's some probability, if I look at the square of that, for transmission versus reflection, right? And so, from the point of view of the particles, I could say I have a random stream of particles with the Poisson process, and I'm flipping a coin with some weight, and it's either transmitted or reflected, right? And that is going to mean the transmitted beam, is it going to be described by a Poisson process afterwards or not? And if so, why? What's your thought about that? Just to make sure you understand my question, what I'm saying is, I have, if I thought about this as a stream of photons with some random occurrence, right? That when I see when I see a photon, it's described randomly by a Poisson process. And now I'm flipping a coin and I'm taking a photon either out in. Yes, what do you think, Matt?
So I would think it would be Poisson on both sides, because now instead of just like you could divide it up into time windows and then be flipping like a low probability coin, right, and then sending one photon. And so now you're just tacking on the probability of transmission. If say you're looking at the transmission.
Exactly. That's the right intuition. At the end of the day, the whole underlying assumption of a Poisson process is that there was no correlation between the events. That's how we got to it. And the fact of just flipping a coin randomly, I'm not going to create any correlations between them. It just stays Poisson, but with a reduced rate depending on the fraction, right? So from this point of view, we see that if it's Poisson, it's going to stay Poisson. And if it's super Poisson, super Poisson, then it's going to stay the same as well, right? So if I had a convex combination of those, so if I started with a state which was some convex combination with a classical probability distribution, a positive Glauber P representation, excuse my handwriting, nice, of that, then if this is greater than 0, there's nothing that this is going to do to change that. It's going to change exactly the same. So linear optics takes classical light to classical light. Now, if we have a little more time, at the end of the lecture, I want to come back to this question about the power of linear optics. Because this statement can lead you down a, well, maybe let's do it now, because maybe it's too important to wait till the end. And when I grew up in the late 1980s and early 90s, well, no, that's when I was in graduate school. This is how I learned about this stuff. And everyone said, oh, linear optics, wow, what a waste of time. There's never anything be interesting with that. But, of course, this doesn't say anything about what happens if the input state is non-classical. Suppose somehow, some way, I started with non-classical light, and then I put it through a linear optical network of beam splitters and phase shifters. But let's just examine that a little bit. So, just to get started, let's say, for example, I have a single photon state. in one mode. Okay? So let's say I have one photon in the ith mode. So that's, I'm going to create one photon like that. Okay? So that's my input state. Let's just say it was a single photon state. What is the output state in this case? Well, I got to do the scattering matrix on the input state. Right? And what is that going to be? Well, my input state is this, which I can write as this, because I can put in a U dagger U, but U does nothing to the vacuum, so that's fine, right? And then this is the sum over So what is that state? How many photons are in that state? One. Right? The optics doesn't change the photon number, it just redistributes it. It's just that photon is in a superposition of modes, right? And lambda this matrix, so the probability amplitude for photon to be in mode J, given it started in mode I. So we sometimes call this the transition matrix, because it's the transition amplitude to go from I to J, right? So that's just saying, you know, if I had some kind of, let me draw this kind of linear optical network as we sometimes draw it, with some number of input modes and some number of output modes, the same number, with some, I'm going to put little beam splitters and phase shifters, so these solid things are phase shifters, those, they're all solid. But let me do it this way. There's a little phase shifter there, then there's output modes, and there's a mirror up here. Okay? So this is, I send in some modes, they bounce around, they come out. If I put a photon in one of these modes, it's going to come out in the superposition of those modes, right? And the transition is exactly what we have for the classical field, right? So we can think about the electric field as kind of the wave function of the photon, right? That's how we've described it. And so this is just saying, in the same way that the electric field I start with an electric field in here, and I have a superposition of the electric fields in all these output modes, weighted by these amplitudes according to that matrix. It's exactly the same transformation, right? So a single photon and a classical field kind of have the same transformation. The reason the classical field does is a little amazing, right? Because it's made up of lots of photons, but every photon is doing its own thing, and the fact that I have multiple photons never plays a role because of the Poisson statistics. But let's say we had something slightly different. Now let's say we have 2 photons, okay? So let's think about, let me get rid of this. Let me say there are only 2 modes. I'm going to get rid of this mode. So let's just put 2 modes in and 2 modes out. Doesn't really matter how many, but let's just do this to start. Do some phase shifters, some beam splitters, in, out. Okay. So let's say that I have, so there's 2 modes, let me label them 1 and 2. Okay, this guy is out 1, this is out 2. So let's say I have 2 photons. I'm going to start with 1 photon in mode 1 and 1 photon in mode 2. This would be my input state. What is the output state now? Well, I can just stick in a couple of U-dagger U's here, so I'll just do it. And that is going to equal you agree? Right? Okay, so what is this going to be? Well, there's going to be, let's just multiply it out, and lambda sorry, I have these guys, I have those guys, lambda 2, 2, lambda 2, 1, A2 squared, plus lambda, okay, so now I got lambda 1, 1, 2, 2, a dagger, 2 dagger, plus lambda 2, 2, lambda, here. Let's see, this is this guy. Oh yeah, that's right, okay. All right? So those are the 4 terms here. They correspond to, for example, this first term corresponds to a process by 1 goes to 1 and 2 goes to 1. That's one possibility. Then they would both end in 1, etc., etc. Okay? Now, importantly, these guys commute. The creation annihilation operators in different modes commute. So I can move this outside here and just write it like that. This corresponds to two indistinguishable processes. In one process, they go to the same mode they started in. One goes to 1 and 2 goes to 2. In another process, 1 goes to 2 and 2 goes to 1. That's another possible history of these two photons. And because they are indistinguishable, these two processes interfere. Right? And this particular sum is known as the permanent of the matrix. So the permanent is like the determinant, but without the minus signs. Okay? So if I look somewhere, we had this matrix. Here, the determinant would be this times this minus this times that. The permanent has the plus sign. Okay. Now, suppose I had n ports like that, this. So now instead of having just two ports, 2 inputs and 2 outputs, suppose I had n inputs and n outputs. So let me say in that case, my input state would be sum over all the, product over all the modes, n modes. Okay. What is the probability amplitude for having one photon in each mode and the output? So I go back to exactly the same that I started. This would be have one photon in each input, and I want to have one photon in each output. What is that amplitude in that case? It's once again the permanent of the matrix, because each one of these things represents just a permutation of the photons. All the different permutations of the photons come with an amplitude. This one permutation is nobody goes to anywhere else. They all started in the same mode they did. Another permutation is 1 and 2 switch places. Another permutation is 2 and 3. All the possible permutations that can happen. For each permutation, I have to write the amplitude for that transition, multiply them together, and that is nothing but the permanent of the matrix. And so the probability of seeing this, to calculate that, would be the permanent of the matrix. Now you say, all right, fine, calculate the permanent of the matrix. That's a really hard thing to do, it turns out. Unlike the determinant of the matrix, which is an easy thing to calculate, especially for a unitary matrix, how would you calculate the determinant of a unitary matrix? You diagonalize and just multiply the eigenvalues together. So the determinant is invariant under a similarity transformation, but the permanent is not. In fact, it is really hard. There are no efficient algorithms to do that. And to calculate that permanent typically would take something with exponential amount of time in the size of the matrix. Yeah.
Is this the boson sampling problem?
That's where we're at. This is exactly where we're headed. So the point here is that if I asked you the following question, given some distribution of photons in each of the input modes, what is the probability to see some distribution of photons in the output modes? You could not calculate that efficiently. That probability generally would take so if you wanted to create a random number generator which would generate random numbers according to this probability distribution, you couldn't do it. You could not sample random numbers from this probability distribution. And as Zach gave away the punchline,
Sorry.
it's okay. It wasn't so funny anyway. This is known as Boson sampling. It was first brought to our attention not by quantum opticians, but by computer scientists Scott Aronson and his student Arkhipov, who knew that calculating the permanent of a matrix was a computationally complex thing and tried to come up with a quantum mechanical problem for which the permanent would be the answer. Okay. Now, I should mention you may have heard about the Google quantum supremacy experiment, right? It's the same spirit. It's exactly the same idea, except instead of bosons, you got qubits, but it's the same basic idea. You want to create a probability distribution that arises from a quantum mechanical interference effect that you couldn't generate random numbers from. And then somehow you have to verify that your output is coming out with the statistics of that. That's a hard thing to do and perhaps not yet proven that they actually did it. But because of course this is the ideal probability distribution. You're always going to have imperfections in your experiment. I'm sorry, but you will. And so you're never going to sample from this distribution. You're going to sample from some nearby noisy distribution. And whether that's hard to sample from or not remains to be seen, in my not so humble opinion. But, you know, the Google paper's complicated. But it's a very interesting point that even linear optics, it would be the last place on Earth any quantum optician would have looked for quantum supremacy, as we call it, in linear optics. I mean, linear optics is trivial. Linear optics is this. It takes classical to light to classical light. You would never, ever think. And that's why, you know, it just goes to show you have to think outside the box. And only people who were never put in the box, you know, could do that. All right. That's fun. Before I just, maybe I should say one last word about this, which is, where is the complexity coming from here? Since this is a bunch of non-interacting photons, right? I mean, why is this thing in any way complex? Isn't every photon just doing its own thing? And we just said each photon just undergoes a classical field transformation. Each one does its own thing. They don't interact with one another. So how is this thing not just single-body physics, which is easy? Which is why the physicists would say this is crap. Linear optics, forget it.
Because they're indistinguishable?
Because they're indistinguishable particles, absolutely right, and that's important. And that came up in this sneaky little step here. We have interference between indistinguishable paths. There's also an intimate relationship to entanglement here. Now, it's not clear at all what the hell this thing has to do with entanglement, but it does. Because if this was a separable problem, then we could just think about them as independent modes. What's becoming entangled here is not the particles, but the waves. The modes are entangled from it. We will see that. And we saw, this was kind of buried a little bit. Or maybe, let's see, it's still around, no. When we had this input-output relation here, we started with this coherent set of coherent states. That's a product state. Each mode is its own coherent state. It's a product of the modes. The output state is a product state. It's a bunch of coherent states. Each mode is in a coherent state. But when I put one photon or any non-classical light of a particular flavor, anything that doesn't have a positive P distribution on the beam splitters, I can't describe it by a product state anymore. So there's an intimate relationship. It's weird that linear optics can entangle things. All right, very good. All right, so now let's talk about our nonlinear optics. So we have this picture over here of nonlinear optics. And so now what we're going to do is, as we started last lecture, and I want to do it a little bit more in detail, is look at the particular problem of what we call three-wave mixing. Okay, these are the things that are associated with chi2. All right. So let's write down what we have here. We start with, let me start with Helmholtz equation. For waves at some frequency. Okay. So Helmholtz equation says L squared plus K squared of the electric field at that frequency. And I'm going to, for the moment, ignore the vector nature of the field. Okay. Is equal to current, the second derivative of the current, and with all of the units in there. This depends on the polarization. Okay. And we're going to just have the nonlinear one here. The linear guy is put into here so that K here at that frequency is the index of refraction omega over C. Okay, so the index of refraction here is 1 plus 4 pi times 1. So that's the permittivity, epsilon, is n squared. Remember Maxwell's equations, maybe you don't, but here it is. All right, so that's my wave equation, where the source now is the nonlinear term. Okay, and particular for three-wave mixing here, let's start with the problem as an example of some frequency generation. So omega, I have two frequencies, omega 1 and omega 2, and they'll add up to omega 3. So let's look in particular here at the stuff that's coming out at omega 3. The stuff that's coming out at omega 3 is coming from the beating of omega 1 and omega 2 together. The positive frequency components of those together, the Fourier transpose together, so I have minus 4 pi over actually let me leave that out for a moment. Come back to that. Okay. All right. Let's. What we do when we solve this problem, what we're thinking about is the following thing. We're saying I have a Chi2 crystal, and I'm sending in these two beams. One at omega 1, the other at omega 2, and then I have some at omega 3. Omega 3, I might also inject it in there, or I might not. It might just come out of the whole process, but here's omega 3. And for the moment, let's think about these as all propagating in the same direction. Okay? So, if we think about this, we make an approximation where we treat these things as plane flat. So I'm just going to think about the evolution along the z-axis, where I have a certain length of the crystal here, L. Then I'm going to write my electric field here as a plane wave with a slowly varying envelope. And that slowly varying envelope is scripty E. Okay. So for example, I have one at omega 1 with a K1, omega 2 with a K2, etc. And my slowly varying envelope is slowly varying in the sense that its change as a function of propagation distance is going to be much, much smaller than the rate of change than the wavelength at that frequency. Okay? So the wavelength might be, you know, some half a micron or whatever, and the rate of change of the amplitude is going to be very slow compared to that wavelength.
Sorry, which wavelength? Like,
whatever the wavelength is here, so K here could be, if this was omega 1, so K is that, and lambda is 2 pi. So whatever frequency I'm talking about for each of those frequencies. Okay. So under that approximation, I can put in this ansatz into here, and I get an equation. When I take this guy, first of all, I'm taking this to be a plane wave in a sense with a envelope on top of that. I'm ignoring the transverse, so this is a one-dimensional wave equation at this point. And when I plug in this ansatz into this equation, when the second derivative hits this, I get minus k squared, and that cancels that. And then I get a derivative on this and a derivative on that 2 different times, and then the derivative on this twice, which is small comparatively. And so the bottom line is I get the following equation. 2I K3, one derivative of the slowly varying envelope at omega 3 is equal to minus 4 pi omega 3 squared over c squared times p. Oops, I have to still have, sorry, e to the I K3z is equal to minus 4 pi omega 3 squared over c squared, the nonlinear polarization at that frequency. Okay. So that just came from plugging in my ansatz and using the slowly varying envelope approximation. Okay, and now you're going to hate me, but that's life, you already do. And I'm going to get rid of that. And I'm going to put the K3 on the other side. And that's going to get rid of one of these and put an index of refraction down there. Okay? And then you hate me some more, and I'm going to move that to the other side of the equation because I'm just too damn lazy to write it all together. Okay? So that's how that amplitude is changing as a function of time. So now we have to plug in for this piece over here, coming from the Chi2 process. The Chi2 process there is the beating of these waves, one at omega 1 and the other at omega 2. Each will have this form, and they'll multiply together. And so what I will end up with is I 2 pi omega 3 over the index refraction at omega 3c, the Chi2 coefficient at that frequency, and then I'm going to have one at omega 1, another at omega 2, e to the I k1 plus k2 minus k3 z. Okay, so what we see here is a nonlinear differential equation which couples three waves, hence the name three-wave mixing. There's the wave associated with laser beam 1, there's the wave associated with laser beam 2. They be together. One of the things they can do is give me a frequency at omega 3, which radiates electromagnetic radiation at that frequency, and the amplitude of the electric field grows as a function of the propagation through the crystal in this way that depends on the two amplitudes of those two fields. Okay? All right. Now, this particular, let's call this amount delta K. Okay. Okay. So now, if we make, all throughout, we make all kinds of crazy approximations. They're not crazy, they're very good approximations, but we make lots of approximations. The so-called non-depleted pump approximation. So under the there will be actually, and we're going to write them down in a moment, three different equations. There's an equation for how the amplitude in wave 3 changes as a function of the propagation. There's an equation for how wave 1 goes as a function of propagation. There's an equation for how wave 2 goes as a function of propagation. And they're all coupled together. They're three coupled nonlinear differential equations. We can't solve them generally because they're linear, in this case ODEs. Really, that's not a partial anymore. It's a full derivative, but who cares? We know what we mean. However, in the non-depleted pump approximation, in this particular case, let us assume that I put in two very intense laser beams, one at frequency omega 1 and one at omega 2. My Chi2 is a kind of wimpy little Chi2. It doesn't do very much. I'm not going to generate much at omega 3. Okay, so I can at that point just say that the amount of energy that I have to take out of 1 and 2 to put in 3 is just tiny and negligible compared to how much energy it started with. And that means I'm not depleting in any way the pump. And I just treat these guys as constants. That's a non-depleted pump approximation. Okay. Related to the intensity times with some phases. Okay. So under that approximation, I can solve this equation because then it's a linear differential equation with just a constant thing. And one finds under that case that this is equal to let's say at the output. Right? That's just integrating that equation from the input at 0 up to the final z equals L. That's just the integral of that. Okay? Integrated that from 0 to L. That's what I did. And I got that. All right? Which, I'm going to do the usual trick. Take out half of that. Multiplied by L on both sides. Put a 2 over here or 2 over there. And that's the old sink function. Everyone loves the sink. My favorite appliance. That's not, but anyway. And so the intensity at the output is proportional to the product of the intensities of the two beams, and then the sink function times the chi2 coefficient, and then the sink function like that. Now, this, you know what this looks like, the sink function, right? It falls off in a way. It depends on the length of the crystal. But what is delta K here? Delta K is equal to K1 plus K2 minus K3, right? Which was the index of refraction of course we have, it was from the whole get-go, the only terms that survived were the ones where this was true. Okay? These conditions together, the fact that this has to be true was from energy conservation. But that doesn't automatically imply that this is 0. Why not? It depends on the dispersion. If the index of refraction is a function of frequency, then that's not necessarily going to match in the same way. But if I could rig it up in such a way that that would be true and set this to be 0, then the system is said to be phase matched. Now, we have to play some tricks to do phase matching because it doesn't happen automatically. The way we can do that is by using the fact that the index of refraction can be dependent on the polarization of the light. And for different polarizations, we get different instances of refraction. So those are the tricks of the trade. For example, I could make this guy polarized like this, and this guy polarized like this, but look for phase matching when this guy is polarized out of the board. So it might be the crystal is such that it has one index of refraction if it's oscillating in this direction, and a different index of refraction if it's oscillating. It's a birefringent crystal. And then I can rig it up that for these things this happens. And that's this particular guy where these two have the same polarization, and this that was called type 1 phase matching because, you know, it's a very creative name. There's also a type 2 where these guys would have opposite in this guy, but whatever. This is not a course in nonlinear optics, and I couldn't teach one anyway. But what we do is we rig this up so it's phase matched. When it's phase matched, then I get this being, when that's true, then I can get, oh, I forgot times L, huh? There's a times L here. So I multiply top and bottom by L. And this guy times L squared. Then I can get a growth in when it's phase matched. All right. So, what the hell does that have to do with non-classical light? Well, let us see. Firstly, let's write down like the general coupled differential equations for 3 wavelengths. So, let's say I have a crystal. It's a Chi2 crystal. And I'm going to have 3 waves. They're not even going to be in the same direction necessarily. Okay. Omega 1, omega 2, and omega 3 in these particular with directions. So then we're going to talk about general derivatives. We're going to assume that everything is phase matched. So we've chosen the directions and the nature of the crystal such that K3 is equal to K1 plus K2. And omega 3 is equal to omega 1 plus omega 2. Then we can do the same slowly varying amplitude tricks, and we can write down 3 coupled ODEs, and here they are. This is the one we just wrote down. I'll just write it again. And I'm just going to write a shorthand now. Call these E1, E2, and 3, which is the electric field as a function of Z at frequencies 1, 2, and 3, okay? So that's the equation we have over there, where everything is phase matched. I've set delta K to 0. Then I'm going to have an equation that looks like this. Let's take a look at those equations, and let's try to understand where they come from. This is the same equation that we had before. We have something oscillating at omega 1, something oscillating at omega 2. You add them together, they oscillate at omega 3. What about this term? Well, this guy oscillates at omega 3. And this oscillates at minus omega 2, right? Because it's got the star, which oscillates with the minus sign. And so this is omega 3 minus omega 2, which oscillates at omega 1. And this polarization density radiates at a frequency omega 1 and generates that wave. Similarly, this oscillates at omega 3. This oscillates at minus omega 1. This is the difference between omega 3 and omega 1, which is omega 2. This polarization density oscillates at omega 2 and radiates at omega 3. And it spatially all co-propagates in a phase-matched manner so that everything stays in phase, hence the name phase matching. The polarization density is propagating with the same wave number as the fields so that they stay in phase with one another and therefore can amplify. Okay? All right, now what? Well, let us, for an example, consider the following problem. Again, these are three coupled nonlinear ODEs. We can't solve them, but we can solve them in some good approximation. Okay? So let's, for example, let us assume that I don't put in let's see what I want to say. Yeah, okay, I can leave it that way. So let's say that this is a strong pump. Let's say this is a UV laser.
The blue is omega 3, right?
It should, yeah. Okay. Back when I was a postdoc, I used some big argon ion laser. I don't know if those even exist anymore. I don't even know what that is, but I know that it broke all the time. So that's some intense laser, okay? And so we're going to take that as a constant. Okay? Yes?
So now we're pumping with
Omega 3. And I might have omega 1 and omega 2, but they're going to be weak. They might be nothing. I might put nothing in omega 1 or omega 2, but these are going to be weak.
So instead of doing some frequency, we're doing down conversion.
Could be, yep, in this case. Indeed. You're right, this is a difference frequency generation, which as Matt said, we would call that down conversion. But I'm not quite going to down conversion yet, right? We'll get there. I might not get that right, but we'll get there. All right. So I'm going to tweet out weak. These guys are weak. This is strong pump. All right, so let's continue. So in that case, I can treat this thing as some constant, which I will call kappa, which is kappa for constant. Because I'm going to take the undepleted and keep that as constant, -3. Okay. So now I have those ODEs.
Is the constant kappa the same for both? Or is there a kappa 1 and a kappa 2?
Oh, that is a good point. There is a kappa 1 and a kappa 2 in this particular example. If I have this guy as non-degenerate, you're absolutely right.
Thanks.
What do you think about those ODEs?
Second kind. Like the hyperbolic oscillator.
Yeah, these are linear differential equations. And in fact, they can be solved. Okay. For simplicity, let's say that we rigged up the phase, although we'd have to do that. I mean, generally, so kappa 1 here, if you look at it, it has a magnitude and a phase. Similarly for this, right? The magnitude of this depends on that, and the phase depends on the phase of the pump and I, right? So this guy over here is equal to the phase of the pump plus pi/2. Okay. Let's say that we, just for fun, for simplicity, set the phase of the pump to be minus pi/2, so that this had no phase. Then we can easily solve these equations. Let's just take this to be 0 for e.g. kappa 1 and kappa 2. How would you solve these differential equations now? Well, I could take the second derivative of this guy. But that is equal to right? And what's the solution to that equation? These are positive numbers now. Just I take the way I've defined this.
Hyperbolic.
They're hyperbolic functions, right? This is like a harmonic oscillator, right? This would be equal to agree with that? Those initial conditions? And this guy, this is E1, this derivative of this guy over kappa 1 is E2 star. Does that look familiar? What is that? That's our Bogoliubov transformation, right? There's an A and an A dagger here. It's a two-mode Bogoliubov transformation in this case. But it's a Bogoliubov transformation. And that just came here from those differential equations, which are the same ones that you see, that you will see in your homework when you look at the Heisenberg evolution of the creation-annihilation operators that describe the squeezing transformation. In particular, if we had the case of what's called degenerate three-wave mixing, Actually, before I say that, I want to say maybe one thing. So this kind of optical experiment could be known as a optical parametric amplifier. Okay, so what do I mean by that? So suppose I have I have some signal. I have some signal I want to amplify. My signal is this green beam. Let's say it's the red one. I want to amplify it. It's some weak beam. What I'm going to do is I'm going to pump the crystal with this strong UV laser. Okay. I'm not going to put in any omega 2. Okay, so this is strong. Pump. And this is my weak signal. And I want to amplify that signal. Well, I have these equations here, right? And I will get a similar equation for omega 2, but let's look at this guy to start. If I look at that guy, what I see is that the intensity in this guy as a function of distance is going to be the intensity times the cosh squared of this coefficient for the particular case that I took this guy to be the way I define my kappa. Okay. And what's going to happen to that? As a function, when z gets very big, this gets exponential. Right. Right. For very big z. So I have amplified that signal through this process, right, with a coefficient kappa that depends on my chi2, right? It's proportional to my chi2 and the strength of the pump. Do this four-way mixing. But you see this exponential growth. Kind of maybe see where squeezing might ultimately come in, as we know that there's this exponentiation that happens in squeezing. Now, there is a similar equation for the other solution. If I were to take the second derivative of this equation and decouple it, it would have a similar equation, right? I would end up with E2 as a function of z is E2 at 0 cosh plus E1 star 0 sinh z. And if I did that, that would tell me is that in the process of amplifying this signal, I'm also going to create inside the crystal a new beam at omega 2. Right? Of course, in this case, the initial condition is such that there is nothing here. Right? My electric field, in that case, for beam 2 is going to be E1 star at 0 sinh squared. This is known as amplifying the conjugate. It's the phase conjugate. But never mind, the intensity that comes out is also ultimately going to be related to the same kind of growth. And so in the process, I generate this third beam at the difference frequency. Omega 1 is equal to omega 3 minus omega 2. I will generate, and in the jargon that you will hear, oh, it's the other way around. I'm generating this guy, pardon me, omega 2, I'm generating as the difference between omega 3 and omega 1. If this is the signal, because this is radio frequency land, this is called the idler. And so when you read the literature on this kind of three-wave mixing process, people always talk about the signal and the idler and the pump. I don't know, this was idling somewhere. I don't know why the hell it was called the idler, but people call it that. You'll hear that language all the time in this kind of three-wave mixing process. Okay, we're going to pick this up and finish it up next time. We're not going to review very much. We're just going to kind of plow through because we need to move ahead. But what we see here is the classical description. We now want to translate this into the quantum description and think about the implications of this for the generation of squeezing and non-classical light. All right? Very good.